big salient points. So we need to be able to assign our oxidation numbers. Officially, the thing at the bottom, our oxidation numbers must add up to the overall charge. That is kind of our big lesson that comes out of dealing with oxidation numbers. So they're very closely related to charge, but remember, charge applies to anything and everything. Oxidation number very specifically refers to a single atom, right? And I would argue the oxidation number should always be calculated, right? Even when it's trivial, so that you get used to that pattern of, oh, it's oxidation number, I have to run through a calculation. Whereas charge, you could just look at the upper right-hand corner, okay? We defined our oxidation being a loss of electrons, or rather a loss of electrons is being defined as oxidation, and a gain of electrons is being defined as reduction. The acronym to help memorize that was? Leo says GER, thank you. So I'll step up on that box again. So with that, where we will go ahead and advance to would be looking at a chemical reaction. So you've already gone through and assigned oxidation states to each of these things. So this should be just a matter of looking at determining which species was oxidized and reduced by looking at the oxidation states of each of the individual atoms. This should be a relatively quick review. So I will let you go ahead and start working on that, and then we'll talk through it real quickly. Once we have all of our oxidation states defined, actually, I guess before we do that, are there questions about the oxidation states that are written up there? Does everybody understand and agree with where they came from? Okay. The next thing you would go through and do is look at each atom and see how it changed. Okay, so we could start with hydrogen. Hydrogen started at a +1 and it ends at a +1, which means there's no change to its oxidation state. It's neither reduced nor oxidized. If we go through and look at the carbon started at a -4 and became a +4. So its oxidation state has changed. We should be going through and defining it as either oxidized or reduced. Before we go through and do that one, we could also shift to the oxygen and note that the oxygen went from a 0 to, well, dang, oxygen showed up in two different places. Ultimately, it doesn't matter because the oxidation state in both those places for the oxygen was -2. So we don't really have to stress about it. And we would again note that our oxidation state has changed. Now that we know our oxidation state has changed, what we should be picking at would be what happened. How did the oxidation state change? That how is a transfer of electrons. So to go from a 0 to a -2, what did you do? Okay, so we can sort of cheat. You're answering a different question, but that's okay. Okay, you just went through and said, I want to deal with oxidized and reduced. And if we look at 0 to -2, what happened to the number? It decreased, or it was reduced. So that is technically a reduction. And if that one's a reduction, what's the other one? Must be an oxidation. So what you're relying, did I spell that right? Oxidation, I think I got it. Okay. What you're relying on there is recognizing how your oxidation states have changed, which is good, that's fine. Okay. But we could also go through and look at how the electrons were transferred. Because I wouldn't be surprised if you get other questions that are along the lines of how many electrons were transferred. So if you just go through and tell me it was reduced, that doesn't answer the question. Right? So what happened to go from a 0 to a -2? Right? Our oxidation state is the balance of protons and electrons. To become negative, could we have lost protons? Doesn't that make a negative number? If I lose positives, don't I become negative? Changes the identity of the species. So losing protons is a non-starter. The only thing we can change is the electrons. And if we're going to reduce, wouldn't that make sense to lose electrons? Right? Because we're reducing things. You reduce the number of electrons. Well, that didn't work out, right? Because if we reduce the number of electrons, what should our charge have become? More positive. So we have to be careful to recognize the sign issues within these systems. When we're talking about that 0 to a -2, what did we actually do? We gained electrons. that gain tends to trigger off sets in our mind that we're becoming more positive, but we have to realize what we're gaining. What are we gaining? Electrons, and electrons are negatively charged. So we have to watch out for those signs. We ultimately get a double negative. In certain scenarios, we don't get a double negative for the reduction. Okay? But that's not how you spell gain. So we have a gain of electrons. We've got our reduction. We've got the GER part of it, which means the other side must have lost electrons. And if we lose electrons, that loss is a negative, but our electrons are also negatively charged, which means our number should become more positive. And that's exactly what it did. We went from a -4 up to a +4. Make sense? Hi. The next part that comes into this is that we go through and we add labels. So we could go through and define what did CH4 act as? What did the oxygen act as? Okay, how did they cause the reaction to happen? Okay, and as soon as we talk about how they cause the reaction to happen, our language is going to change a little bit. Because if we look at what happened to our carbon, what did we say happened to it? It lost electrons, and it was therefore oxidized. Okay. What did it do in the process of the reaction? We could go through and say, well, it was oxidized, but that's not describing its action, that's describing what happened to it. So instead, if we want to describe its action, what did it do? It caused something else to be reduced. Okay? Which sounds really strange, but that's ultimately our definition behind it. What was its action? Its action was causing something else to be reduced. Something else had to be reduced because what happened to it? It was oxidized. Causing something else to be reduced sounds kind of goofy and convoluted, so instead we created a word for it, and we described that as a reducing agent. This tends to add all sorts of layers of complexity behind this, or confusion, because the thing that was oxidized is reducing, yet its action, it's causing something else to be reduced. Right? So you have to ensure that you maintain kind of that flow all the way through. Okay? The analogy I tend to use is now probably way too old of a reference, but if you looked at old school comic books, Mad magazine, you got spy versus spy, how they fight each other. We're looking at effectively a spy versus spy situation here. Okay, so the name is going to swap on you. Okay, so we got to be careful with that. If we go through and look at what happened to the oxygen gained electrons and therefore was reduced. What was its action? It took electrons from something else. It was the oxidizing agent. Okay? And what we're looking at is effectively the English language being nasty with conjugations of the words. Okay? So we've got to be a little bit careful with making sure we understand reducing agent are our opposites. The other term that you'll hear come out is ants. So the reductant or the oxidant. Okay? They're what caused. That was the action that they forced to happen. Okay? So it's the opposite of what actually happened to them. So we have to be a little bit careful within our labeling system to ensure that we don't lose track of that language. When we're talking about the agents very specifically will only refer to one side of the equation. They will refer to the reactants. So oxygen in this case is the oxidizing agent. Methane, CH4, is the reducing agent. Kind of, sort of? Okay. For me personally, I find it very easy to get these things confused. So whenever I go through and do these kind of oxidation reduction reactions, I will define the oxidation states for every single atom. I will then go through and identify whether it was a loss or gain of electrons. If it was a loss of electrons, I'll write oxidized right next to it. And then I will also write reducing agent. So the amount or the volume of stuff that's written underneath the chemical equation whenever I do these is rather extensive because we're looking at all of those individual pieces. That way I can ensure I'm not trying to hold it in my head, because if I hold it in my head with those simple swaps back and forth, I'm probably going to screw it up. Okay? So my recommendation is to write it out. Kind of like when we look back at our past units, if we're going to go back and do quiz retakes. One of the first steps that we should go through and do is a chemistry class. We should write out our chemical equation. With that chemical equation there as my centerpiece, I can now base stuff off of that. Okay? If we're talking about the past unit, Unit 3 and Unit 2, both of them involved equilibrium. So not only am I going to write out a chemical equation, but the next thing I'm going to write out would be the K expression, my equilibrium, so that I have that content defined for me. If I start reading questions before I've identified that, I will likely screw up how I'm going to place that information. So if I can get my information down first, as clean and pure as possible, if I'm getting it wrong after that, that's my own bloody fault. Okay? Now it's not a confusion of the question, it's because I literally didn't know the content. Kind of, sort of? Okay. So, how can we use this? Breathalyzers, hopefully you've never had to experience this, but breathalyzers are testing alcohol in your breath. So if there is alcohol in your breath, when you breathe into the breathalyzer, it reacts with dichromate. Okay, dichromate is Cr2O7. Okay? In that chemical reaction, it does an oxidation and it changes the oxidation state of the chromium. It also changes the oxidation state of the alcohol. Okay? But when we change the oxidation state of the chromium, it changes colors. Okay? So we can then compare the amount of that color change back to how much ethanol was actually present in your breath. We then run correlations and tests to say, well, if you had this much alcohol in your breath, that likely means there's this much alcohol in your bloodstream. And that's how they're testing it. Okay? So it's based off that color change through a redox reaction. Kind of, sort of? Why is that powerful to know? If you know how a test is run, can you potentially circumvent the test? I'm not saying you can, for the record. I genuinely don't know. But if you understand how something works, you now have the ability, okay, particularly if you're being tested on it, to work around it. If you had all the test questions, can you circumvent the act of learning the content? Yeah. You just tell somebody to tell you the answers, and you just memorize the answers and write the test down, right? Okay? So if you understand that process, it can change how you manipulate systems, which is potentially useful. It's also potentially bad, depending on how you're using it. Make sense? Okay. So if we go through and look at this chemical reaction in a little bit closer detail, what is oxidized and what is reduced in this chemical reaction? If you remember our discussion Monday, right? When we talked through Monday, we said we had to be a little bit careful with our chemical formulas because determining the oxidation state of the atoms within a chemical formula could be misleading because we could have one element, carbon, have different oxidation states within the same compound. Right? And the only way we'd be able to differentiate that is by doing what? Looking at a structure. Okay? Which is why we have structures drawn out here so that you can evaluate those oxidation states. Okay? So this is a blue box. You need to go through and work through this. What I would recommend you do, okay? Number one, determine your oxidation states just based off of formulas. See how that ties out. What does that turn into? And then also go back and determine the oxidation states for the elements based off of the structures and see how it changes. Does that make sense? At least some head shakes, yes. So we should now have a whole bunch of work up there, assuming I didn't do my math wrong, which could be questionable. We should be okay. If we go through and look at the work that I've written out, this work is written out focusing on the chemical formulas, not on the structures. Did anybody go through and do it for the structures? Really? Nobody. You did it for okay, thank you. A little bit. A little bit. You got the first one done?
Yeah.
Cool. So when you went through and did the first one, we'll call it carbon 1, carbon 2. Your hydrogens are ultimately going to all come out to be the same charge, and your oxygen will come out to be the same charge, right? What'd you get for carbon 1?
I did them together. Wait, no, negative 2.
Carbon 1?
Wait,
Should I do that math? I'm trying to do the math in my head. You said negative 2. I accept. Carbon 2?
Also negative 2.
I don't accept that.
No, okay. I might have been wrong then.
Okay. So looking from the chemical formula, let's process how we would do it. Carbon 1, carbon brings in 4 valence electrons. Carbon 2 is also going to bring in 4 valence, so we'll track that work. If we go through and look at carbon number 1, how many electrons does it own? So we go through and evaluate each of those bonds. Is carbon more electronegative than hydrogen? Yes. So it owns that pair. It owns that pair. It owns that pair. So it owns 6. Okay. Does it own the pair in between? No. How do we count those electrons? We do.
Oh, by 1, you're right.
Okay. Because it doesn't own them, but the other carbon, the other atom next to it, also doesn't own them. We share those evenly. They each get 1 from that, which means carbon number 1 owns 2, 4, 6, 7. Carbon number 1 should come in at a negative 3. Right? What happens with carbon number 2? Well, it's going to own the hydrogens. We can color carbon number 2 slightly differently. It's going to own those hydrogens, so there's 2, 4. Okay? It only owns half from that bond, so it gets 1, so it's got 5. What about the bond with the oxygen? Oxygen owns them all, which means that carbon owns 5 electrons, which means negative 1. Make sense? That's how we process going from the structure. If we go through and look at the formula came in at a negative 2. Why did it come in at a negative 2? From the formula, we're assuming all the carbons have the exact same charge. Okay, so ultimately what we're doing is we're assuming the average. What is the average between a negative 1 and a negative 3? Negative 2. That's why the numbers align. Does that make sense? Okay. Depending on how you get this, you're going to potentially see, well, but you're going to change your systems. Ultimately, you're not going to change the systems. What you'd end up discovering is that when we look at carbon 1 and carbon 2 in the product, one of them doesn't change. The other one does. Okay? So if we go through and look at the oxidation states as defined within all the formula work that we've got written out, okay, following the same pattern all the way through, the number of times the element shows up, for the sake of the recording, the number of times the element shows up times its oxidation state, okay, we're always assuming that it's unknown or we don't know it, times the number of times the next element shows up, that's a 6 corresponding to the hydrogen, times its oxidation state, plus the number of times the oxygen shows up once within that formula times its oxidation state, and that equals 0. And as we talked about on Monday, okay, that's 3 unknowns with 1 equation. We can't solve that until we provide a little bit more information. What's that little bit more information? Oxygen, what we've defined as wherever it went, Z, is always going to be a negative 2. Is it always a negative 2? No. When is it not? When it's bonded to oxygen or fluorine. Those are the only 2 cases. Okay? Since it's not bonded to oxygen or fluorine, we're looking at a negative 2. Okay? What happens with the hydrogen? The hydrogen will very commonly come in at a plus 1. Okay, why? Because when we talk about hydrogen, it's usually bonded to something more electronegative than it. Okay? If hydrogen's bonded to a nonmetal, your electronegativity difference is already defined. Your hydrogen is going to be lower in electronegativity, which then means the hydrogen comes in at a plus 1. With that extra bit of information, we can now sub those numbers back into our expression, which is what I attempted to go through and do within those systems, and we get an oxidation state for the carbon coming in at negative 2. We repeat this process for each of our reactants. And note, we're going to get a lot of oxidation states through this system. Right? If we're going to define what was oxidized and what was reduced and our oxidizing agents and reducing agents, we would then need to compare those like oxidation states across, or those like elements across the equation. You'll note for oxygen, which we said was a Z and the Y, with our hydrogen, I've got NC next to it. Why NC? What happened to the oxidation state of our oxygen? It did not change. No change, as in NC. That's kind of neat, right? Lazy. Hydrogen, we can do the same thing. We'll find out it doesn't change as well. We can then double back and look at what happens to our carbon. Okay? The carbon went from a -2 to a 0. How do we go from a -2 to a 0? Okay? And depending on what we've got memorized, right, that's going to be slightly different. But to go from a -2 to a 0, am I becoming more positive or more negative? More positive. What does that mean I had to have done? I had to have lost electrons. And if I lose electrons, I'm looking at a way to skip steps, but that's okay. Oxidation, which would be the reducing agent. Make sense? Okay. What else could we go through and do? Well, if we have something that was oxidized, that equally means we have something that was reduced. So we could go back through, and our purple structure, we defined that X to be the oxidation state for chromium. For our green structure, it was a trivial one. That's our oxidation state. What changed there? We went from a +6 to a +3. How do we go from a +6 to a +3? We had to have gained electrons. And if we've gained electrons, that means it was reduced, which means it was the oxidizing agent. Remember how I said I show lots and lots of freaking work? Ta-da! Okay. This is what allows me to keep track of those individual numbers and process this all the way through while minimizing as much as possible mistakes. Okay? Even then, I have problems with left and right. I have problems with -2 going to 0 being gaining or losing electrons. Okay? So I have to go slowly through that system, and I would recommend you go slowly through it as well. Make sense? Okay. Is there another way that we could have answered? Yeah, the whole thing, actually. Of course there is. So can I erase everything? Some people are drawing or still writing, so I won't erase it. Okay. We defined oxidation and reduction. We defined it by gain and loss of electrons. We also defined it in a historical context. What was that historical context? Oxidation sounds like oxygen. So what we talked about for oxidation was increasing bonds to oxygen. And reduction is decreasing bonds to oxygen. Take a look at your carbon, particularly carbon number 2. What happened to the bonds to oxygen? It increased. So what happened to the carbon? It had to be oxidized. Once I've defined it as oxidized, I know it's the reducing agent. What happened to the chromium? It lost oxygens, which means it was reduced. So we have two ways that we can check this. We can go through the gory detail numbers, which more than likely you're going to have to do. But you also have a backhanded way of doing it by just going back to those definitions, historical definitions of oxidation and reduction. Okay? Those historical definitions don't always work, but again, oxygen is so flippin' common that most of our redox reactions will involve oxygen, so it gives you an internal check. If you want it. If you don't want it, it's still there, you just don't have to use it. Make sense? Questions? Okay. What is electricity? It's our movement of electrons. It's ultimately our flow of electrons. Okay. Why is that not showing up? Oh, that's interesting. It shows up on, oh, there it is. Okay? So we've defined electricity as the movement of electrons. Okay? Interestingly, when we look at this definition, I have a feeling she wanted to draw something, and I don't know what she wanted to draw. Okay? It doesn't say it's just the movement of electrons. What does it say? And starts the whole frickin' sentence off. Chemists. You talk to a physicist, changes. Okay? Sometimes with engineers as well, it'll change. Okay? Because what we're talking about is how ultimately charges are flowing. Okay? And depending on who you talk to, you'll get different references depending on how they've defined what electricity is. Okay? So it can be very confusing to talk with people from different fields, particularly when you move into things like semiconductors, because they won't talk about electrons moving, they'll talk about holes. What the hell is a hole? The place where an electron was. Okay? And if you find that confusing, that's probably because you've taken more chemistry than you have of any of those other classes. Okay? So depending on that context and where you end up, you may hear references to electricity being something slightly different. Okay? Ultimately, it's the same concept. If an electron moves one place, okay, if I start with a wire and I have an electron moving this way, what forms over here once the electron has moved? A place where the electron was, which we could call a hole, and ultimately that hole would be positively charged. Okay? So you could look at electrons moving one direction, or you could look at holes moving the other. Okay? It's strange. Just be aware that there's other language systems out there. I'm sure there's a reason they do it. I just don't know what it is because it doesn't make any sense to me because I've been trained as a chemist. Okay? So if we go through and look at how batteries generate electricity, what's happening is we're running a reduction and oxidation reaction. That reduction and oxidation reaction talks about the transfer of electrons. Okay? But we set it up in a very special way. Okay? What was reduction? Reduction was gaining electrons. And what was oxidation? Loss of electrons. So if we consider what's happening, the electrons are moving that direction, right? They move from our oxidation side to the reduction side. Okay? And if that happens, what electricity do we get? See, if I phrase the questions right, the answer is lovely. It's perfect. Yeah, we get nothing. Okay? What we would get is whatever's happening in the oxidation starts to decompose, and whatever's happening in the reduction starts to form. Like, woohoo, that's exciting. We can use that for different purposes, like electroplating. Okay? But that doesn't get us electricity. So what do? We put a barrier in between. Okay? That barrier prevents the electrons from going from the oxidation side to the reduction side. But not only do we put a barrier, we put a nice, thin, conductive piece of wire that goes all the way around. Okay? So now what happens? Our oxidation can ship electrons into the wire. Those electrons can ship back around to the reduction side where it can gain electrons. That's now causing the electron, the flow of the electrons, to move through a different system, moving through that wire. And that now is electricity. Okay? We do the exact same thing conceptually with dams. Okay? We've got water flowing down the mountain. Okay? Water flowing naturally down the mountain. I know it's flowing up in the diagram, okay? But our electrons are our water flowing naturally that direction. What do? We put something in the way to force the water to do something for us in the process, okay, of it naturally doing that action. Okay? So our batteries navigate this for us. Okay? This kind of a cell is known as an electrochemical cell or a voltaic cell. And that's what we get to study for most of this unit. Okay? When we talk about it, since we've put that barrier in place, what we need to do is look at each of the separate parts of the reaction. We need to look at, the reduction side of it and the oxidation side of it. And I apologize for weird font stuff. Okay, since we can split these now into half reactions, we'll call them half reactions. One of them is reduction, one of them is oxidation. That physical separation is what I leverage to allow for the electron to flow. Okay, so what I'm hoping is that when that oxidation reaction happens, that these electrons will now flow through my wire. I need to loop it the other direction. Flow through my wire over to the reduction side, so that the reduction side can complete its reaction. That wire is now giving me a place where I can insert something to cause a desired effect. Okay? Cause a light bulb to turn on, cause a motor to spin. That's that point of that process. Okay? But this only works if there's a proper balance or favorability of that chemical reaction. Does zinc give up enough electrons to reduce the copper? Well, it's 2 and 2. Shouldn't it be fine? Okay. But we have to remember we're in 152. And in 152, we talk about the extent to which a chemical reaction happens. And we measure that extent and we quantify that extent. We look at it as equilibriums. So when we go through and deal with that, what we have to do is ensure that when we put these two equations together, the net result is a favorable what's a favorable reaction? Fast could be a good thing, but that doesn't describe the favorability of the reaction. I love that you went fast, that's good. What's the other aspect? Spontaneous, the thermodynamics. So we would need to know something about the energy of each of those reactions. And that when the energy of those half reactions add together, do we get a spontaneous system? So what we're evaluating is effectively the thermodynamics. Okay? But we don't call it thermodynamics anymore because this is electricity, not chemistry, so we have to invent a new system. Okay? So instead of talking about delta G's, we talk about E's, cell potentials. Okay? Those cell potentials are extremely related back to delta G's. Okay? They're slightly different circumstances because we're looking at how those electrons are transferred, so we get new unit systems, we get new calculations, we get new formulas to go through and quantify them. But ultimately, it's the same concept. How do we stack those two reactions so that we get that favorability? It's a spontaneous reaction. Because if it's non-spontaneous, do I get the electrons to move? No, I would have to put energy in. The whole point was to do what? Get energy out. So it has to be a spontaneous system, which then means we're going to have to go through a system of quantifying all the energetics of these individual reactions and tying that quantification back to the concepts that we already understand of thermodynamics and delta G's and equilibrium expressions. Hooray! Okay? So, our voltaic cell uses that spontaneous reaction to release energy. It's that release of energy that we're trying to capture, okay, and manipulate the way we want. So if we set up this reaction, our oxidation, okay, is going to shuttle electrons through the wire over to the copper solution. Okay? The copper ion in solution now sees a surplus of electrons at the surface. So what does it do? The copper ion reacts with those electrons to make copper solid. Okay? So what happens in this system if we were to evaluate this? Our electrons flow right over to here. What happens to the charge on the left-hand side? It's going to lose electrons. This side is going to become increasingly more positive. What's going to happen on the other side? It's going to become increasingly more negative. Okay? What we're generating there now is a large potential that wants to neutralize out. We don't like charges. Okay? Said another way, what we've generated is effectively a battery. I'm going to pretend that's, I don't remember which side is positive or negative. Let's call that side a positive and that side a negative. Is that a good enough battery? Okay. Does the battery produce electricity for us? I just hold the battery near my device and it goes, duh, charge. No, it doesn't. What has to happen? I have to create a connection. So here's a connection to my light bulb. So now I've got that connection. Do I have my light bulb? No. What else has to happen? I have to connect it back. Why? To balance out the flow of electrons. I'm trying to neutralize the positive at one end with the negative at the other. And if we just looked at our voltaic cell, we're talking about forming charge. Is that going to happen? No, there's something missing from our voltaic cell. That voltaic cell needs a way to neutralize that charge. The electrons aren't going to flow because all that's going to do is generate more charge on either end. That's a problem. Okay? So we've got the basic components down, but there's something missing behind this. Okay? And I think I've jumped ahead a little bit. Okay? Before we get too excited into how we would fix our voltaic cell, let's just assume it works. Write the overall redox reaction occurring in this voltaic cell. Okay? And then you can also discuss at your tables which direction the electrons are flowing through the wire. Kind of already told you that. But what's the overall reaction look like? Coming up with that overall redox reaction does seem to stump people a little bit. Okay? But what I would argue you could do to help kind of trigger hopefully some thoughts from past experiences, genuinely thoughts from 152 should appear, but I honestly don't remember what those thoughts are. I would do this. What have I done differently? I stacked them. Why would I stack them? 2 halves to a whole. And what I could now do is go through and add them up. Everything on the reactant side of that arrow should be on the reactant side. I'm going to take my zinc solid plus my copper plus 2 plus my 2 electrons. We'll come back to that in a second. On my product side, I have the zinc plus 2 plus my 2 electrons plus my copper. That should be really familiar. That should look an awful lot like, we did do this. Hess's law stuff in 151 and the things we did earlier in this semester that I wish I could name, but I vaguely remember that we did them. I think we did a review of enthalpy calculations, which was Hess's law, and some entropy calculations. We just added the 2 equations up. So that would be our overall equation. But just like in mathematics, if we have an overall expression, can we simplify it? Yeah. If something shows up the same on both sides, what can we do? We can cancel it out. What's my overall expression? Zinc plus copper ion goes to zinc ion plus copper. That's it. That's my overall expression. Okay. So what we're trying to acknowledge is how those 2 reactions work. Can you get that from the 2 separate equations? Yeah. The reactants on the, I already forgot that side, reduction side? Oxidation side. I meant to talk about this one. And the reactants on the reduction side are reactants. So put them on the same side of the expression. Okay? The products on one side are the products on the other. Put them on the same side of the reaction. And what we end up with is the same overall reaction. If we talk about the electron flow, how is the electron flowing? Okay. Do I need electrons flowing into the zinc? If we look at what's happening to the zinc, do I need electrons coming in? No. What's happening with the electrons? They're going out. It's a product. Right? So we can use the directionality of those chemical reactions to help us understand that flow. Kind of, sort of? Okay. Yep, let's look at the bottom. Determine the oxidation states. This half of the classroom, do SO2. This half of the classroom, do calcium sulfate. Okay? And if you're like, I don't know which half I am, do them both. So we can look at the longhand version of the work. Okay? Our sum of our oxidation states have to equal the overall charge. So if we're looking at the SO2, our overall charge is 0. 1 times x, so I can get away with just x. I've got 2 variables and 1 unknown, except that oxygen, I know, is the second most electronegative element, which means it's always going to steal the electrons, which means it's always going to be a negative 2. So x minus 4 equals 0, and I get x equals plus 6. Okay, just checking. At least one person listened. X equals plus 4. Right? Sometimes I just want to hear a response. That's all it is. I'm lonely. Right? X equals plus 4. What happens on the calcium sulfate? Right? We could go through and do it the exact same way. Right? And that is fair. But you'll note that what I went through and did is this little dotted line. Why can I do a dotted line with calcium sulfate and I didn't do it for the SO2?
Is the SO4 like the compound? I don't know what it was.
Why we don't care about the name? What? Who said it? What'd you say? Ionic. Since it's an ionic compound, I can split it into the individual ions. Okay? Calcium, being a group 2 metal, is always a plus 2 in an ionic compound, which means I'm looking at calcium plus 2. The SO4, if you didn't memorize the charge for SO4, hopefully you at least got calcium. And if calcium was a plus 2, to balance it out, the SO4 must be a negative 2. Okay? You can then go through and evaluate those as independent pieces. So for the calcium, my oxidation state is going to be plus 2. For the other one, I've got this 2 variables, 1 equation issue again, except oxygen is always a negative 2. So I get x minus 8 equals negative 2, and I get x equals plus 6. Ooh, see, the 6 came back. Right, and we get x equals plus 6. Everybody track? Right. Which molecule is the sulfur more oxidized? I'm not going to lie, I have to think about that one a little bit. What was oxidized? Okay, lost electrons. So if it was more oxidized, what does that mean? It's lost more electrons. Okay, which means the number should be bigger. Okay, bigger gets a little bit dangerous, so I would argue more positive. Okay, as long as you keep them straight, it doesn't matter. Which number is more positive? Plus 6 is more positive than plus 4, which means our calcium sulfate is the one that was more oxidized. Make sense? Cool. Moving on. When are we done? We started at 8:30? Is that right? So 45. So here's a slightly larger version of the periodic table of oxidation states. We did already talk through this, but it turned out that Dr. Schneven didn't like her initial periodic table either, and so she went and found the same table that I did, trying to call attention to the oxidation states. There's a link earlier in the lecture slides, so where you first see this table, there's a link for it. Right? Again, I find it real questionable to call this trends in oxidation state. Okay. So, which way were the electrons flowing through the wire? Okay. To the right works. Our electrons are going this direction. They're coming up from the zinc, and they're going into our copper. Right? And if we're going to look at our overall reaction, ta-da, we've got the overall reaction. So it's like we're continuing that content. Okay. The next thing that we could go through and do is label anodes and cathodes. Okay? Why would we go through and add extra terms? Because electrochemistry was an old concept of how we dealt with these things, and so we started labeling the pieces. Instead of being positive and negative, we labeled them as anodes and cathodes. Why? I don't know. It's just what we did. Okay? The electrode where the oxidation occurs is the anode. Okay? So I want to tie those two things together. Okay? So one thing that you might do is you could say anox. Right? anox, like the language, anox, which makes sense. You can't say an red. Why can't you say an red? When do you use the N when talking about a subject? Ooh, I didn't use the end. A subject, not an subject. If you say an subject, you sound stupid. When do you use the N? When there's a vowel. Is R a vowel? No. Is O? Yes. Anox. So the anode is our oxidation. So which side of the reaction had the oxidation? Except multiple answers for that. The gray side, the zinc side. Yeah, okay, yeah. Don't get all excited. So we've got our anode. Right? The electrode where the reduction occurs is called the cathode. Do we have another stupid thing we could do with that? Red cat. Okay? Because red oxes never happen, but red cats you see all the time. Right? Actually, that's kind of true, like the little ginger cats. Right? I'm going to call them red. People with red hair, it isn't red either. It's orange, right? So. We can't call it a straw cat. That doesn't work. Okay, so the other end will be our cathode. Okay, make sense? Okay, so those are extra labeling things that we need to be aware of as we go through and navigate things, because you'll hear things where there's, what's happening at the anode? You're going to have to go through and say what your chemical reaction was to be able to tie back to the thing that's happening at that anode, okay, or that cathode. Okay, the last thing that needs to happen within our voltaic cell. So remember the little stupid picture that I drew with our battery, right? Everybody remembers my lovely battery? Okay, we don't get the light flowing through there, or we don't get the light until we complete the circuit. Okay, we have to get our electrons to cancel out. Okay, our charge to cancel out. And if we looked at our initial setting without this middle piece, well, now it just bleeds everywhere, but that's okay. Our electrons move up and around. But if they move up and around, we start to build charge at those individual sides. That charge doesn't hold. Okay? Our electrons would actually stop flowing because it's building too much charge. We need to neutralize that charge somehow. And so the way we do that is we incorporate what's known as the salt bridge. The salt bridge will allow for the flow of ions in between. Those ions are the counter ions. Okay? Counter ions are the things not in our chemical reaction. I can't go to the shelf and pull off zinc ion. It doesn't exist. Okay? But I can go to the shelf and pull off zinc sulfate. Okay? Why? Zinc ion itself is charged. That's unstable. It needs a counter ion. And since it's positive, it needs a negative. So I can pull zinc sulfate off, dissolve that in the water, and I now have my zinc ion as my reactant for my chemical, or sorry, not my reactant. I can put zinc sulfate in there. Okay? What happens with the other side? Well, where do I get the copper ion? I can't pull copper ion off the shelf. It has to have a counter ion. Okay? So that counter ion would be another negative thing. Okay? But if we only had negatives in that solution, what's going to happen is we would only be able to move a negative thing through. What we'll also add is usually another counter ion that's positive to help balance that charge. And so what's going to move through that salt bridge is the ions in the opposite flow of our electrons. Okay? That will help to mitigate that charge. Remember, if our electrons went this way, this side starts to build a positive. Okay? Because it's starting to build a positive, what ion has to move towards it? Remember, I have to neutralize that charge. The sulfate will need to move towards it. What ion would need to move away? The sodium would have to move away so that we're canceling that charge. Okay? Take a look at the other end. We're starting to bring electrons into this side, right? So that would start to build a negative. What needs to move away from my cathode? The negatives. My sulfate needs to move away. Interestingly, it's flowing the exact same direction the anode needed it to flow. That's because that's how it works. Okay? And if I'm starting to build that negative, I could have the sodium ion flow towards it. Okay? So we could talk about how those salt ions can shift back and forth to balance out our charges. Okay? Eventually what happens, all of our salt ions have moved to opposite ends, and we can't now navigate or counterbalance that charge shift. What happens then? The battery's dead. Okay? We can't negate that charge flow, which then means the battery stops functioning. Okay? So we need to have those ions in place to allow this system to go through and function. Okay? Oops. Get out of there. What is that? Ooh. That was going to be dangerous. This is so painful. Okay. So how do we know how much energy is released? So we sort of touched on this. To get that energy, we have to understand something about effectively our thermodynamics, the spontaneity of those individual chemical reactions. Okay? Instead of referencing it as a delta G, because it's kind of different, this is where we bring in the concept of our standard cell potential. The cell potential has a symbol of E, right? We know it's standard because we have that stupid little not symbol or our zero in the upper right-hand corner, and we know it's the cell potential because it says cell next to it. So this E, more or less, probably a little on the less, is supposed to somewhat represent our delta G. Okay? It's related to it is where we should actually go with that. Okay? Standard cell potentials, standard conditions. Of course, standard conditions, we know temperature would be 0 degrees Celsius, because that's what standard temperature means when we talk about standard temperature and pressure. Except this says standard temperature is 25 degrees Celsius. Why? Different scientists defined the standard. And because different scientists defined the standard, it's not fucking standard. Okay? We'll assume 1 atmosphere pressure, at least everybody's consistent on that one, and then the concentration of all our reactants and products is 1 molar. Okay? That will become important because we can leverage that concentration to make what's known as a concentration voltaic cell. Okay? So just having salt move across a salt bridge can actually generate electric power. So if you're trapped out on a desert and you need some electricity, find a bunch of coconuts and fill them with salt water. Okay? And you can play around with concentration gradients to generate electric potentials. We'll talk about that later. Okay? The chemical potential is the energy per unit charge, and this then gets measured in volts. Why did we say it was related to delta G? What units are delta G? Kilojoules. Our cell potential is measured in volts. Why? Different scientists. Okay? Different scientists create a different unit system, which then ultimately means you will be responsible for converting those unit systems. Hooray, conversions. Okay? So we've got tons of standard cell potentials out there. They're all, or not all, but most of them are recorded and reported so that we can go through and look at these tables of cell potentials. Okay? Because we could look at an oxidation or a reduction, that would change the sign of the energy, right? If we look at the forward reaction versus the reverse. Okay? Since we want to be as consistent as possible, we picked one. So we picked reduction. So when we talk about our cell potentials, they're by default given as the reduction cell potentials. Okay? So if we go through and look at it, we'll see the half reaction for the reduction form. Because it's a reduction, what happened with the electrons? It gained electrons. Yeah, there we go. See, I should start growling more. It works better. Okay, we gain electrons. That gives us our cell potential. If we now want to calculate the cell potential for our voltaic cell, how do we go through and do this? Okay, well, in our voltaic cell, what was our overall reaction? You all wrote it down. I'm hoping I'm doing this right. I don't remember. Was this right? We'll find out if I'm wrong in a second. But you're all saying I'm right. So okay, cool. So what I want to do is take my half reactions and I want to manipulate them so that I can get that cell potential. Remember with Gibbs free energy and enthalpies, we could do like adding reactions. Guess what you can do with cell potentials? You could do the same thing. That's kind of cool. So if I go through and look at this, the copper ion is where in my overall reaction? On the reactant side. So what I can do is take my cell potential, whoops, that's fine, I'll just put the electrons on the other side. Okay, and my cell potential, whoops, not the delta. My cell potential for that reaction is 0.342, technically volts. Right, where's my zinc? It's on the product side, but I'm given it with it on the, sorry. Our zinc is on the reactant side in our overall equation, but it's in the product side in the given equation. So what do we have to do? We would have to flip the equation. And if we flip the equation, you flip the sign. Okay, so our cell potential was given at negative 1762 volts, but since we flipped the equation, we bring in another negative sign. Right?
Yeah.
Now what do? Add them up. And you now get the cell potential for the reaction. Okay? For a spontaneous reaction, what should your delta G be? Negative. Did that make sense to you to have negative to be spontaneous? I mean, some people would look at it, well, why would you want it to be negative? Like, aren't positive things better than negative things? Okay, so the person that went through and said the negatives for delta G, that was kind of weird. What happens with our cell potentials? They're positive, because the person that went through and did it defined those systems so that the good results would be positive. Those are ultimately definitions on how we've decided to run our calculations to navigate those systems. Okay? Why does that become important to us? If we're going to relate our E to our G, what are we going to have to watch out for? We're going to have to watch out for a negative sign floating in that expression somehow. Okay? Foreshadowing. Did anybody do the math? 1.134? 0.04 volts. And we now have the positive cell potential for this battery. So if we link these two together, we get enough to power not much of anything. We get effectively a normal battery. Okay? Kind of makes sense? 5 minutes. See where we're at. Foreshadowing. Look at that. Okay? I swear I read the slides, just not in order. Our cell potential is going to be related to our Gibbs free energy. Okay? And as we just stated, when we looked at a favorable cell potential, the favorable cell potential was positive. A favorable delta G was negative. To have this equality work, we have to introduce another negative. Okay? So this is something that we're going to have to watch out for when we deal with the relationship between our cells and our Gibbs free energy. Okay? You'll note we have other parts of that conversion. Why do we need other parts? What were the units on delta G? Cool, yep, absolutely kilojoules. And our units on cell potential were volts. Actually, we got a response there, cool. Those units aren't the same, which means we need a conversion process. That's our N and F. What are the N and F? The N is the number of electrons transferred in each reaction. Remember how when we did the chemical reactions, okay, just knowing that it was oxidized or reduced wasn't good enough. At least that's what I said earlier on. And I said one of the things you're going to need to know is how many electrons were actually transferred in that process. Why? Ta-da! We need to know that number because that number must insert into our expression for relating cell potential to Gibbs free energy. Okay? The F is Faraday's constant. Right? Faraday effectively went through and created a conversion system that allowed us to relate volts to kilojoules. Right? That unit system is using C. What is C? You get another unit, that's coulombs. Coulombs, I believe it's coulombs times volts equals kilojoules. That's the unit conversion. Okay? So we're going to have to be able to manipulate this expression and deal with solving and subbing in all those numbers. Okay? These are, based off of past experience with your quizzes, the equations are given, not necessarily the meanings. Okay? So it may not be a bad idea to write your equation down and then make sure that you know what each of those letters mean so that you can deal with solving expressions. Make sense? F is going to be extra special. I don't know that I've seen constants. I don't remember seeing constants on your front of your quiz. So that might be one that you want to go through and write down. Because I'll fully admit I have never memorized that one. All right? So you need to have that number so that you can run your calculations. Make sense? Okay. And I'm a little nervous right now about delta G, this expression. I don't know if this is actually coming to joules or kilojoules. I think it actually comes to joules. Okay. So calculate the delta G for the voltaic cell where zinc is oxidized and copper is reduced. How would we go through and do this? Well, what's our delta G calculation? I got 2 minutes. Okay. Do we know the E cell? Yeah, that was the 1.104 volts. Cool. Do we know F? 96,000. I'm cheating. 485. Thank you for allowing me to cheat. Coulombs per mole of electron. Our cell potential 1.104 volts. And then we would just pull our N, negative N, from the equation. How many electrons do you see in the equation? Okay, so there's a couple different answers that can float here. Number one, I would say none. There are no electrons in the equation, but you're now making an interesting point. How many electrons were needed in the equation? 2. So we are talking about the transfer of 2 electrons. How do we know it was 2 electrons? Technically 2 moles. So we could try and play with the charges. You do have to be careful. What if I went through and said it was copper 3? It still says positive 2, right? So is it 2 electrons? Well, it says positive 3, so it must be 3 electrons. Also no. 1 electron. Also no. How would we figure out how many electrons were transferred? Do we have a way of, say, perhaps taking our overall expression and splitting that into partial equations that we could then figure out how to add them up to get to our proper overall equation? And those partial equations, since we're looking at probably half of the equation, copper plus 3 going to copper, and our zinc going to zinc plus 2, we might refer to those as half reactions. And if we go through and try to balance our copper 3 going to copper, what did we have to do? We had to gain 3 electrons, and if we look at the zinc, what had to happen? It had to lose 2 electrons. If I added those 2 up, would the electrons cancel? No. Are electrons stable? No, which means electrons cannot appear in the overall equation. How can I add these 2 up so that the electrons cancel?
Multiply the red by 2, and then the bottom by 3, so you get 6 in total.
So now how many electrons were actually transferred?
6.
6. The number that I would drop into that expression is 6. So we have to be a little bit careful about where we're pulling the N from Make sure you're paying attention to your equations to ensure that the electrons are canceling each other out through your chemical expression. When we've got charges, that makes it easier because you can see lowest common charges. But realize I didn't have to write copper +2 or +3. Okay? I could have written copper chloride. The charge disappears when I convert it into that overall formula. Okay? With that, we're going to go ahead and stop. And we'll pick up there.